Welcome to this video about the Wicksteed power hacksaw. We're going to spend 25 minutes or so looking at this 8-inch capacity hacksaw I call Hacksaurus, as it's large, ancient, and depending on the blade fitted, has big teeth. It was made in the 1950s and is a well-used machine which has been repaired and repainted several times in its life. On buying it, this was described as large, old, noisy and dirty, but working. At least it's clean now. I think the 1931 patent number is for the hydraulic control unit. Here is the control for the hydraulics with 4 positions. To run in position, raise the blade, cut materials, and lower the blade. And the hydraulic unit itself, the down pressure on the blade is controlled by the dial on the left and the ram can be seen on the right. The down pressure is provided by the weight of the top section and is resisted by the ram to reduce the force to the required level. This hydraulic pressure counterbalance controls the weight on the blade and not just the speed of descent as with a damper. The hydraulic unit then lifts the blade on the return stroke to prolong the blade life and helps clear the cuttings. Power is provided by a 1 3/4 horsepower Brook motor running on 415 volt 3-phase. Here it is mounted on these fully adjustable motor mounts. It's a 1950s motor and is probably original. Here is the matching contactor, but this MEM isolator is a later addition. Here is the vise. It is adjustable for miter cuts. There are preset holes for bolting the fixed part of the vise, or the curved slot can be used for fine setting. We had better do as it says. Let's prepare the machine for use. First, I'll fill the 4 oil cups for the saw bow slides. This whole top part pivots on the pin at the back. These oil cups are for the pivot. Now the first shaft bearing. Under these covers are tubes that take oil down to the second shaft bearing. The 2 eccentrics that power the hydraulic unit. And the other bearing for the second shaft. Now the other first shaft bearing and the eccentric for the suds pump. These are grease caps for the motor. Screwing in the caps pushes grease into the motor's roller bearings. Over to the other side now with the grease gun. Greasing the nipples on the rod connecting the pivoting part of the saw to the ram. Checking the oil level in the hydraulics. Yes, there's some. There's no provision to lubricate the small end, so I just splash oil at it occasionally. The big end has roller bearings. Now setting the suds pump flow rate. Here is the rod for the suds pump in the bottom of the tank. If the level goes too low, the piston at the bottom squirts fluid out of the tank. We're ready. Let's have a do at making it go. A fine blade is fitted, so let's cut some thin-walled section. You'd have to be pretty foolhardy to cut anything with this marking unless you were totally sure it was empty. The steel spacers are needed because of the welds protruding at the ends of the bottle. The wall thickness is 2 mm and the steel is fairly tough. Now we will look at the blades. This is a fine blade with 18 teeth per inch like we've been using for the thin section material. Coarser blades can be used with larger material, and the larger gaps between the teeth, the skips, clear the swarf more efficiently. These are more usual for this size of machine, with 6 teeth per inch and 4 teeth per inch. A coarse blade can cause problems with thinner section materials. Although the hydraulics on this machine should prevent it, the blade can drop down when the material goes into the skips of the blade and the cut will judder badly, resulting in a bent workpiece and broken teeth. A finer blade will alleviate this problem. Here is an intermediate blade of lighter pattern. These produce a thinner cut and less waste. The difference in height means that the stop may need to be adjusted to ensure a complete cut. This is done by loosening this nut and turning the threaded prop. This so-called Super HSS blade is a cheap unbranded false economy. They do not last well or work well. They haven't even bothered to round the ends. This is a 14-inch blade, which is probably the most common size for a workshop hacksaw. And here are some 12-inch blades from a very small hacksaw. This one is an unusual make. If we compare a 12-inch hand blade to a 12-inch machine blade, we can see that they are far too light to use, even though the hole centres are the same. Some modelers' saws will use them. Although this 16-inch blade looks enormous by comparison, they do get a lot bigger. Blades come in two main types. Bimetal. A strip of HSS is welded to spring steel backing. You may be able to see the join here. And all hard, where the entire blade is HSS. These are supposed to be more accurate as they flex less, but they can snap. Bimetal blades don't snap, but in my experience, rather than snap in half, chunks of teeth break away, rendering them useless anyway. This part is spring steel. Used quality blades are a good source of materials for other projects, as can be seen by this one, so don't throw them away. I may show some of these uses in another video. There is some possibility of sharpening the coarser blades if they're undamaged. All branded blades, regardless of type I've used, work well enough, but avoid unbranded ones. I'll fit a coarser blade now and cut some larger material. This one has 4 teeth per inch. Power hacksaws cut on the backstroke, so the teeth point backwards. I'm sure some power hacksaws differ. As a rule of thumb, the machine cuts towards a fixed part of the clamp, in this case at the back. Adjustable spanners do have their uses. This knob tensions the blade. With a little tension, the pins holding the blade can be tightened down. Now the tension can be set and locked with this nut. I'll use these as spacers so an unused part of the blade comes into play. Without spacers, you would rarely use more than half the blade. Checking the blade has been fitted squarely, as if it does not sit flat it causes a lot of problems. As the teeth are offset, the cut is measured from a tooth protruding towards the end of the bar. A machining tolerance is added to allow for run-out. This will do. Increasing the down pressure for the larger material. 70 seconds to cut a 2 1/4 inch mild steel round is largely in line with the manufacturer's estimate. Now let's cut something approaching the maximum size for this machine. This is 8-inch diameter mild steel. Let's try fast gear. Going back to slow to preserve the blade. Now we'll have a look at the pieces that have been cut off. You can see a large burr is left. I've already removed the worst of the burr here with a file. Both pieces have cut reasonably cleanly and squarely. I will need to remove this burr. There are a few marks on this one showing where the blade has dragged. Unusually, it has cut more than 1/8 of an inch off a square. Maybe because I kept stopping and starting the machine for the video. It will need a bit of extra lathe work. This is what's left afterwards. The swarf needs to be cleared away, otherwise it dries and rust welds itself to the machine. All the swarf brim-filled a 2-litre tub. With the machine cleaned and oiled, you can see the cuts in the table where it has previously run out. All of these predate my ownership. This brings us to the end of the video. Thank you people, I hope you enjoyed the show.